Do I have to mute my... No, is it fine as it is?
You unmute your mic.
Is it?
Yeah, it's unmuted, so it should be fine.
Okay, good.
So hopefully people can hear us. Yeah. And there is no HDMI signal, of course. Okay, so share the screen. Share the screen. Share the screen.
So it's here. Share your screen. This one, yeah.
Good.
But it doesn't want to be entire screen.
Or maybe window.
So should I... Oh,
Maybe, is it in a Chrome tab, your presentation?
Oh, God.
Can you open it in a Chrome tab, your presentation?
That is a Chrome tab.
Ah, it's a Chrome tab, so
Yes.
you can go here instead. You can close this, go here, and open the tab. It's available.
There are a zillion things open, of course. Do you see the... Let's see. Do you... So this is meat. No, we'll never get
Can't
it.
find this.
I don't know. Can I can quit everything and
Yeah, maybe
reopen just
open
this
this
one?
in a new window.
But this is not gonna cut it right, so I can drag this one. It's also not.
You can copy this link and maybe open it in a new window with your
So-
presentation. Just the presentation and this tab.
So then I quit
Yeah.
Chrome.
Share the presentation. Yeah, entire screen, sure. Yeah, now can you go to your presentation?
Let's see if no it works.
Yeah, so we can now okay. Great, thank you.
Thanks a lot.
Yeah. Great, so ready to go at the great, so great pleasure to have Matteo Brunelli. So Matteo got his master from the University of Milan under the supervision of Matteo Weiss. And then he moved to Belfast, working towards his PhD in the Department of Technology there with me and Gabriele De Chiaro. He was then around, no, he has been around quite a bit, no? Because he moved to Cambridge, joining the Sloan camp, and his group at the time in Cambridge, and then Switzerland, working with Christoph Brugger and Patrick Potts.
Yes.
He is now since a few months.
Well, more than a few.
It's nearly a year.
Yeah, close to a year in August.
Okay, so collaboration with France, working with chiral. And Matteo has developed expertise in quite a few topics from binaural mechanics, non-linear physics, all the way to chiral systems and non-reciprocal phase transitions. He's an enthusiast of physics and one of the most intelligent person I've ever met. So, Matteo, thank you so much.
Very nice position you put me in. Oh, thanks. Thanks, Mauro, for inviting me over. Thanks you for being here. And yes, today I thought I'd like to tell you a bit about the effects of non-reciprocal interactions in quantum systems. So I should maybe start by saying what I mean by non-reciprocal interactions, and I try to put a sketch here to answer that. So by non-reciprocal interaction, I mean interactions like the one between Fox and rabbit. So you might say that the fox experiences positive attraction towards a rabbit, but the converse is very much not true. So the rabbit feels a very strong repulsion towards the fox. And this asymmetry or non-mutual behavior is what I mean by non-reciprocal interactions. And like in nature, we don't see the fox and the rabbit like staring at each other as standing still. Typically, we would see the rabbit running away and the fox chasing it down. So this is to say that typically, as a general features, these non-reciprocal interactions lead to a non-static, non-stationary behavior. And if you want, what I want to ask in this talk is, in a way, if quantum systems could behave a bit and evolve a bit like a fox and a rabbit. And good. To give you some context, I don't know, I think that non-reciprocity in quantum systems in general is a topic that I have been recently interested in. In fact, one of the topics I'm most interested in. And I think that it comes in different shapes and forms. So try to give you a bit of a highlight and then to narrow it down. So one, I know that some people, but in this audience for sure, some people are acquainted with how non-reciprocity appears in quantum matter. For instance, one could take non-Hermitian Hamiltonian with some bias topping. This is, let's say, a Nelson model, and this non-Hermitian Hamiltonian accounts for the dissipation, but neglects fluctuations. One option could be to ask to how to upgrade these to open quantum systems, so to have a Lindblad description, non-reciprocal Lindbladians that also accounts for the role of quantum jumps on top of dissipation. And I've been working on some of these systems. In particular, for bosons, it emerges a connection with amplification, and this amplification has topologically robust features. Or there is, I would put it in a different category, so one can also see non-reciprocal features in systems that in principle can even be closed systems, so unitarily evolving, with boson extended systems. This would be, let's say, a lattice of bosons, where non-reciprocity is achieved by interfering hopping processes with parametric processes. It also exists in the absence of Temerar's asymmetry breaking. We call this quadrant of non-reciprocity, and there are, let's say, exotic models, for instance, a bosonic analog of the Kitaev chain that falls into this category. And not myself, but the experimentalist, so with optomechanical systems, as Mauro said, work at implementation of this. Then I think that a very interesting and exciting direction is to consider systems like of this form, or maybe one has a Lindbladian that describes directional non-reciprocal dynamics, and one asks if how this non-reciprocity competes with many-body interactions, for instance. So one can consider a model like this, but in this case, this plot is for a chain of spinless fermions, where there is some non-reciprocity multiply, and then maybe some density interactions. And one check whether this is really a new class of driven dissipative open quantum systems. And finally, one can also consider the case where the interaction themselves are not reciprocal. And in this case, for instance, and this is what I'm going to focus on, is where maybe you have two ensembles of atoms, and you use the light to engineer a non-reciprocal interaction between. So we would like now to think of these as two populations that interact non-reciprocally. And as I said, out of these many facets, I'm going to focus on this last one. So the things I'm going to talk about, I've been working on these projects with Tobias Nadolny and Christoph Loser, both from University of Basel. It's a pleasure to acknowledge them, and you can find more details about what I'm going to say in these two recent works. And good, so I'll try to provide some background, some context, and for me the context is really about active matter. So active matter is field that studies the property of many-body systems, classical many-body systems that are made out of active particles. If you want, are made by agents as opposed to passive particles. And there are many examples, some of them, let's say, biological examples. So it could be a flock of birds or people, human crowds, down to possibly single cells. So, for instance, these experiments, these are starfish embryos, and this can swim or spin, at least, they put in, say, water, and spontaneously over the span of an hour, they would just gather together and lock in a sort of, they call it a living crystal. This is a super sexy name. And this living crystal would pick spontaneously a chiral, for instance. That's it, or rotating anti-clockwise. But there are also non-biological synthetic examples of one. So there are, for instance, spinning magnetic particles immersed in viscous fluid, or implementation with robotic materials. And irrespective of the synthetic versus biological nature, so common features of these systems, of active matter systems, is that they often support the emergence of also beautiful spatial and temporal structure. And the distinguishing feature is probably the fact that active matter breaks is out of equilibrium individually, so individual agents break Bethe balance. Typically, maybe, I don't know, out of equilibrium matter can be thought as boundary driven. If you want, you should think of active matter as being bulk driven, so each element takes some energy. This could be in the form of food, or in this case, this robotic crystal. So you see each atom is powered by its own motor. So, and they would say use this active system, use this individual intake of energy to then convert it either in motion, so self-propulsion, or in exerting forces one upon the other. And these forces don't have to obey Newton's third law, so action-reaction principle. So this is where the non-reciprocity comes in. In fact, I think that non-reciprocal interactions among active agents, where again, by non-reciprocal means no mutual character of the interactions, have been recently studied quite a lot in the classical context. And this could be, for instance, two forces, as in the case of binary mixtures of colloids, or could be asymmetric rules, let's say like in theoretical ecology or population biology. One example that I'm going to use for the rest of the talk is the predatory dynamics. This is clearly non-reciprocal. There are also examples from the trying to model social behavior. And towards the end of the talk, I'll try to make a connection with also a model from social dynamics. And recently, there has been an attempt to try to understand the properties of non-reciprocal interactions from statistical physics point of view. So let's say, in particular for me, I'm highlighting this seminal work. There are others. This for me was a work that caught my attention. So this was a mission for Sharp from the group of engineers in Italy in Chicago. So in this paper, they studied the statistical properties of classical language systems that would interact non-reciprocally. So, and again, they considered one non-reciprocal versions of standard non-equilibrium problems, for instance, blocking, synchronization, and matter formations. And the idea is that if, let's say, the couplings are reciprocal, you would have alignment or anti-alignment kind of physics, while if the coupling between the particles or the agents are non-reciprocal, you tend to enter in a dynamic sort of configuration. So static order is destabilized. And if you want, my question is simple, so I would like to see if something like that can be said, or what can be said about quantum systems. And I would like to try to say a couple of things. So one thing is that it is in fact possible to engineer non-reciprocal interactions in quantum manifold systems and like into populations of atoms and make such that they behave a bit like a fox and a rabbit. And then, briefly, I'd also like to try to provide hopefully something that is almost a complementary perspective, so meaning that you can also start off from a system that is, well, in this case, atom-driven and put in a cavity, and the small tweak that would be, let's say, an implementation of a so-called superradiant laser. It doesn't matter too much, but let's say a small tweak to this model that would be, let's say, driving only a fraction of these atoms would lead to a situations where you can say a description in terms of non-reciprocal forces, non-reciprocal interactions emerges rather, even though different from here, you didn't put them by design. You didn't try to design non-reciprocal interactions. So I would say that this, for this, let's say, this non-reciprocal interaction can also be a nice interpretative tool. Very good. So I'll start with the first thing, and I'll just go directly into the model. So the model that I'm considering is made of so there are two populations. So population A, population B. Each population is made out of a potential two-level systems or quantum spins. So these time plots, and each of the spin is driven. So in again master equation jargon, I'm thinking that there is locally on each spin of each of these populations, so there is an equilibrium boundary process. And this again is because I want to mirror this feature of active matter where each agent is driven. So I'm thinking to each quantum spin as an active quantum agent, if you want. Then there is a coupling that I would call intra-species coupling. So let's say that each spin of species A, they all talk together. So these are all these like all-to-all connections. And same for B. And how they talk together is via dissipative channels. So this B is a standard dissipator. The coupling of the strength of this intra-species coupling is this B. And this BS is a collective spin operator of all the spins. And now I would get to the more I would call VAB interactions from A to B, and VA interaction from B to A. And when the two are equal, so the interactions are reciprocal, when VAB and VBA are different, I would say the interactions are non-reciprocal. And in particular, the interesting case is when VAB and VBA, they would take opposite sides. So in particular, I would try to stress this, referring to this case as antagonistic kind of company. And it is also convenient, I will use it to define the sum and difference between C plus and V minus. And again, I'm calling this the reciprocal part of interactions and the non-reciprocal part of interactions. You can make sense of it because if, let's say, it's V minus is 0, then you see that VBA and VAB are equal. As soon as V minus is different from 0, VAB is different from VBA, and finally, when V minus dominates over V plus, so the non-reciprocal component dominates, we have this antagonistic coupling. And so the way we can now think of this process that I now sketch with figures, with the arrows, is to use cascaded point of interaction. So that is, so these interactions starting VA from A to B is going only one direction, and so it's in the other direction. So from quantum optics, we would model it with a cascaded process that is direction A to B, and another cascaded process that has the opposite direction B to A. That's kind of it. So here I'm just rewriting the master equation. So these are this interspecies coupling that would couple the two species, A and B, and then we have one Hamiltonian and the open drive and the species within each coupling. So this master equation, as I wrote it, is not in an ended Lindblad form, but it can be cast in a Lindblad form, and provided that this constraint is obtained. But the reason I wrote it in this cascaded, maybe not so common form is that because then this really connects with the implementation of this system. So I mean, then thinking how this model can be realized, so by mediating these two cascaded dynamics, we work with chiral. So one, so we have our collection of octals A and B, and then these are coupled to chiral waveguides. So these arrows represent the chirality of the waveguide. So you have to think that when atoms from a species relax, the excitation will be collected in a waveguide, but can only travel in one direction, cannot operate in the other direction. And this excitation can be reabsorbed by the species B, and the bottom waveguide has the opposite pattern. The crucial aspect is that there is a phase shift in between the two paths. And this phase shift, this I phase shift in this case, is really responsible for this minus sign here as opposed to the plus.
I think at the beginning of the application, that condition B rather than B plus is the condition for being in a Lindblad form. How should I understand that?
If you can, I don't know if I have a backup slide, maybe yes. Yeah, okay, so this is the equivalent Lindblad form. So then you would see that you want this object to be positive, and that is where the constraint steps.
Otherwise, you would have
correct. Yeah, so that is if you want, let's say, minimal stuff, but one can, if you say, set up as to be certain constraints. So one can also think about say, braided geometries, so to allow for adaptive transfer space, reminiscent of giant atoms of couplings. In particular, here, let's say there is this is either cavity or bidirectional standard waveguide that mediates the reciprocal part of the interactions, and this chiral the braided configuration, braided coupling mediates the non-reciprocal part of the interaction. This will allow for achieving this B minus and the non-reciprocal portion of interactions to be larger than the species part. again, it's not too important. I also wanted to just stress that overall this could look like, let's say, a coupling that is mediated by a coherent feedback loop. In that sense, I think that there are even experiments that one would like to think about in more detail that would implement already something I understand is not too different. Particularly, there are works by the group of Philip Troitman in University of Basel, where they would interface, in this case, in an optomechanical system with atomic ensemble, but via what I would call a coherent feedback loop. In this case, is mediated by lasers in free space, so not by chiral waveguides, but you see there is a phi element, and I think that it's not exactly the same models, but I think there are some connections with, in general, coherent feedback loops. And good, I introduced the model, and now what I can try to do is to extract some physics out of it. So the first thing that one might want to do is to, let's say, consider a mean field ansatz, so neglect all the correlations. And I think this gives a very useful picture because one can appreciate the fact that the non-reciprocal interactions really involves the phases. It's among the phases of the space. And the phases are these phi, and they are the azimuthal phases of the on a block sphere representation. If you factorize all the correlation and get to the equation for these azimuthal phases, the dynamics gives you these couple set of equations. And now I can try to say comment on the relevant terms. First of all, these are not exactly, but are closely resembling a non-reciprocal version of the Kuramoto model. So this Kuramoto model is one of the standard models for synchronization. And this is in fact a non-reciprocal version of the Kuramoto model, which is exactly one of the models that was studied in this paper here by Michel Fouchard et al. So at the mean field level, the fact that we get a similar physics would already tell us that there will be some non-reciprocal effect on synchronization. So that is the physics that we have to understand. And then, so there are two terms in each of these equations. So let's say, if you see here, these couples the phases A and J within each species, so this label is the same, and this within B. So these terms, in fact, is coupling at B. So it's the intra-species coupling. So and this kind of tendency to align the phases within each ensemble. So provided that the coupling is larger than the pump strength, I would always put myself into this parameter regime. So what you get is that you achieve synchronization within each ensemble. So you have that if you want all these phases, they would lock to spontaneously breaking U and symmetry. They would lock to a common value of the phases. And I will choose these parameters. And once you do that, then the dynamics between these macroscopic values of the phases, these log phases, is determined by the second terms in the equations. And in particular, so what we know is that this VAB and VBA can be different because I arranged for these fancy interactions. And so now I want to study this mean field level. What is the effect of changing the varying VAB and VBA on the value of the phases? So
the approximation symbols, because they jump from mean field, is that?
Say it again, sorry.
You have the approximation symbol.
Yeah. So there are
the approximation is the.
There are extra multiplicative factors like SA plus, but these are not that they do not qualitatively change the dynamics. But these are in the form of extra multiplicative terms, not additive terms. What is important to know, I'll come back later, is that you see there is an SC that multiplies everything. So this means that if you want to have repulsion instead of attraction between the phases, it's important if population is inverted or not inverted. This connects then to if you are in a lasing regime where population is inverted, you promote attraction between the phases. If you are in a if you don't drive spins, so you promote anti-alignment. And so I would say that now we'll try to explore the phase diagram of the model in terms of these phases. This is how it looks like. And again, so on the try to walk through it. So there is on the x axis the non-reciprocal factor of interaction, on the y coupling the reciprocal factor of interaction. And maybe we can start from a point where interactions are reciprocal and say we can be here in this light blue region. In this case, VAB and VA are equal and are positive. So in this case, there is mutual attraction between the two phases. Phases tend to belong to a common value. So for instance, we have plotting the evolution over time of the two phases. In gray, there is the phase difference. You see the phase difference goes to 0. And this, for instance, this was the case that has been studied by Holland, Thomson from Gila, synchronization between two chromosomes.
Sorry, the reference energy is the intra-species interaction.
So here is like the dynamics between the phases.
Sorry?
So this is the dynamics among the phases. Okay. So there is no direct notion of.
In the previous equation you showed in the blue field, there's also the energy, the interaction, intra-species interaction.
Yes, so I'm always considering the case where this V is that exactly. So here in this case, probably it's set for, or so it's let's say if V is large enough, there is synchronization within each species. So let's say I think that qualitatively, what is important to know is that V here is large enough. And if V were to be lower, you would also see a transition from an unsynchronized regime into a synchronized regime. And maybe I can tell you a bit about how and one can move, for instance, still being reciprocal, but going to a negative value of A plus. So in this case, we have still mutual interactions, but now we have mutual repulsions between the phases. So the phase try to be as further apart as possible. And again, so you see that this ends up in, let's say, this gray line, where the phase difference is still a static configuration. Finally, the more interesting part is when I crank up the non-reciprocal coupling and I put it sufficiently large to enter the orange region. And in the orange region, what I have is that, so you see the kind of evolution of the phase, and you see that there is, so there is, the phase keeps winding in time, so there is a stationary configuration, and in fact, the situation is one where, let's say, the phase difference is kind of locked more or less actually pi over 2, so there is this kind of motion. So one phase, that is exactly the kind of rapid predator dynamics that I mentioned before. So there is this blue phase, once is repelled, feels repulsion from B, but B is attracted towards A. And so there is, if you want, you can think of it as, let's say, a dynamical frustration. So they don't want to settle into a steady state. One wants to always run away, and the other one to get closer. So the situation that we ends up with is a dynamical configuration. And this is one solution. But another possibility is where is one where the chirality is reversible. We run in the, let's say, clockwise sense. There is no, the equations do not distinguish between these two configurations, and this configuration, I'll come back to it later, are related by a parity-time transformation. So entering this traveling wave regime corresponds to also spontaneously breaking a parity time. So, and this, people would call it maybe a classical time crystal. Some people can call it.
So these two waves here, the difference of the phases keep on, it's always the same, it's a constant.
It's a constant, yes. It's not always pi/2, so depending on where you move in parameter space, but it's a constant. But when it's not a constant, so it's also, and you see this darker orange region. So in this case, there is, we call it modulated traveling wave phase. So when that is like a phase where the phase difference is no longer constant. There is, I don't really know how to, they do something like that. So there is also some extra modulation. But I think that there are interesting features about this phase that I'd like to explore more. But let's say, I think that I will focus on this region where time translational symmetry is spontaneously broken. Very good. That is what happened at the thermodynamic limit. So this model is like mean field class. So the mean field is exactly thermodynamic limit. But I showed you before that this comes from, I cooked a Lindbladian, an open system that implements this model. So one can try to understand the origin of this parity-time symmetry that we see in the equation of motion of the mean field evolution at the level of the Lindblad. Again, here I'm not, instead of writing down the equations, I'm just using sketches. So, and there is a very physical way of thinking about parity-time symmetry in our system. So the parity part is like swapping the two species. So here, exchanging the B and the A. And the time reversal part, so the T part of the PT symmetry, is given by reversing the chirality of the waveguides. And again, if you apply sequential in P and T, so you end up in this configuration, which is exactly what you started from. So you can think of it of parity time in this model as in this way. And if you, rather than doing sketches, you implement this transformation on the Lindbladian level. So you would see that this parity-time transformation coincides with the complex conjugation of the UV. And again, I'm not entering details. I just want to say that this fact has physical consequences. For instance, one might want to check at let's say, for instance, spectral densities, so Fourier transform of two-point correlation functions for the spin. So, for instance, going beyond the stationary state, so also in dynamics, and the fact that there is parity-time symmetry as a weak symmetry of the Lindbladian entails that the spectrum, for instance, is symmetric to the omega minus omega branch. That would be the spectrum that results to cut on a cut here. Again, one can see that so the static version that is only a zero frequency DC response of your system. Then you hit the transition point, and here coincides with an exceptional point of the spectrum, and then you have two branches. So you have that, and this fact that you have a frequency plus omega and a frequency minus omega again means that your system has, let's say, one clockwise mode and another mode that goes into the opposite. So the fact that in the spectrum, for instance, you see features two frequency plus and minus omega appearing can be related to the fact that, let's say, the spectrum, for instance, gives information about the density matrix, which is an ensemble, an average over an ensemble, so an ensemble of those ensemble quantum trajectories. And each of these quantum trajectories can be associated with a measurement time. So what I'm going to try now is to try to connect the, let's say, mean field trajectory with the ensemble picture that I gave before by looking at single trajectories in my analysis. In particular, let's say I would consider the case of heterodyne detection. Again, it's not too important. So here I am sketching the time evolution that I had before, that we got to the mean field level. Now I'm just considering, for a finite-size system, I'm looking at a realization, a single realization of a trajectory upon of the light of the two characters. Again, this is a revolution. I put myself in a situation where in the mean field I would have a static solution. So when you see that this looks very much like a noisy version of the classical trajectory. And now I can do the same for a point where the leaf dynamics produces this time translational breaking time crystal-like phase. And so I'm again plotting an instance of a single trajectory here, and you will see that again. So there is some noise dynamics, but still at the single trajectory level, we recover this chase and runaway motion. And you can also maybe see that at around time 20 in these units, there is a change in the chirality, right? So before the winding is in one direction and the chirality flips. So this flip of the chirality is really induced by the measurement, by the measurement direction. Again, this happens for a single trajectory, for a finite-size system. And something that is really interesting then to check is try to explore what is the statistics of this chirality, of the chirality reversals. And again, so that is what that shows it. So for N-50, for instance, here I'm plotting the phase. The phase now is like unwrapped. And this is a bunch of trajectories, and I'm only highlighting one in the dark color. You see that, let's see, phase grows and then it increases, and each of these points corresponds to a flip in between the phase, what I call before parity reversal. Now I can increase the number of spins in each ensemble. So go from n equal 50 to n equal 100. So we would see that the reversals decreases. So it's like arrows marked by these blue marks here. And again, if we increase it again, so we see that the chirality reversals really decreases up. And you have to think that this, like the thermodynamic limit, I would really have no chirality reversals, and I would have completely stabilized one chirality versus the other chirality. In fact, if I plot the number of chirality reversals versus, you can see here, versus the number of particles, you will see exponential suppression of the chirality reversals. So I don't know, I think that this was really nice to see how the many-body interaction stabilize the semi-classical crystal that emerges in the thermodynamic limit.
Do you see this behavior with chiral?
We see, so we tried with homodynamic unraveling as well. We see something similar, but way more nuanced. So it has a really different, thanks for the question. It has a really, so because the physics here is like U1 symmetric, like, and heterodyne detection respects a lot this symmetry, while homodynamic detection is really like asymmetric in phase space. So we see some, for instance, an exponential decay of the the number of time reversals, but it's more rich, it's richer. So there are more features in the. In fact, for instance, with homodynamic detection. So this all I show here is heterodyne detection. I just say homodyne detection is richer, but overall, I'm not showing anything about homodyne detection here. But the fact that the kind of unraveling you do impacts the physics that you get, I think is also, let's say, a nice feature. Say, the most quantum-like feature that I would see in this model. And very good. So the conceptual summary of this is that I'm also extrapolating a bit, so I'm generalizing. So I'm clearly I use a specific model. Here I'm trying to say that this could be more of a recipe for other kind of systems, where maybe you have, say, not exactly the model that I show you, but say a bunch of something that would be an active system. Here, there should be a notion of, I think, local gain, but let's say this could be two genetic systems, and this kind of antagonistic coupling can be mediated by these two chirality, so two waveguides with opposite chirality and phase in between. There is, I think, if you have a model as that, you almost automatically get that the Librarian has a certain symmetry to it, so that is well captured by this parity-time symmetry, and this has consequences on the dynamics, both at the ensemble level. So, for instance, one can see that at the ensemble level, this PT is embedded. This comes it's a feature of the model. This can be seen both. I showed you an instance of two-time correlation functions, but one can also see it in equal-time correlation functions. Not second order, one has to go here in the order. Doesn't matter. So in this case, one will see an average of two different chiralities. But one can also look at the trajectory expression. In that case, I think that there are two ways in which the single trajectories spontaneously affect the PT symmetry. One way is to go into the thermodynamic limit. One would see the emergence of the classical time crystalline-like order, so spontaneously making PT symmetry and time translational invariant symmetry. Or one can check for finite system size with single trajectories, and also at the single trajectory level, one would see spontaneous making of time translational symmetry and PT symmetry. Good. And then I briefly want to say, connect to the second thing that I like to talk briefly about. So here I just rewrote in the mean field limit, thermodynamic limit, mean field description, thermodynamic limit, equations of motion for the coherences of SA plus and SC plus. And so this again is telling me how the component S plus depends on S plus itself. So these are the intransmission things. So the incoherent part would in fact decrease the coherence, and then I can increase the coherence with the intransmission starting P. And you see in these off-diagonal elements, I would say that, and it's another way of showing this, but the interactions are antagonistic, where the sign of the two objects of the diagonal are opposite. So what I said up to now was this case. So this case corresponds to the fact that for the reason that I'm putting incoherent pumping in each of the spins, so in the long-term limit, the spins are localized at a fixed value of C. And therefore, so this SZ is positive for both. And then I have this chiral waveguide geometry that I engineered that allows me to have V minus VAB and VBA to take different sign. But now, guided by this matrix-like form of the interaction, I could also see that if what I want to have is these two to take opposite value, I could also think that I can take the AD and VBA to be positive, so meaning not having to engineer these fast interaction dynamics and having, let's say, the SZ part that is responsible for giving me an opposite sign. So let's say that could have the SZ of one species to be positive, but the other to be negative. This, if you think about it, could really mean that you only drive one species, so you make positive on average only one component, so you probably drive to only one, and the other one would just be naturally relaxed. So again, this then would correspond to having, let's say, your species A that is part, that is an ensemble of atom that is driven, and a species B that is an ensemble of atom that is not driven. And so this would be another way of looking at the what happens with the initial ensemble. Other people give to the very same model the name of a superradiant laser. So you have a bunch of atoms in a cavity. So these atoms are all pumped individually, and the cavity is fastly leaking. So different from a normal laser, the coherence is stored in the atomic part because on average there is less than one photon in the cavity field. And now, so that would be a model that would implement a single species. And now, I mean, the idea would simply be to drive a fraction of the atoms, so out of all of them. So in this way, the driven fraction which would encode this second population that I showed here. And this also for me was very surprising because at least to me, so if I were to say, take a guess, you have a number of n atoms that are driven now in the cavity, and now you drive only a fraction of those, 90% of those. I would have said that the undriven atoms just behave like passive spectators, and maybe the overall output power is reduced in proportion of the number of atoms that are not driven. But in fact, it's completely different. Is that the undriven atoms interact non-reciprocally with the driven atoms. Again, this has consequences. For instance, if you look at the emission spectrum, this is like the emission spectrum in frequency against the fraction of driven atoms. So if the driven atoms are 100%, this is the case. So you would have what you expect from a standard school. Yeah.
When you consider the undriven atoms, the fraction of undriven atoms consists always the same atoms. So are these atoms in the cavity, or you also consider the possibility that a driven atom at some point in the dynamics gets out of the driven region becomes an undriven one and vice versa?
No, the first one. So let's say
so if I drive one, I always drive one. Yeah.
Correct. Yes. What is important though is that let's say they all collectively couple to the cavity. So
yes.
So, but only a fraction of those is
the fraction.
But there is no dynamics within. No. Exactly. Yeah, so if you drive all the atoms, then you are back to the standard superradiant laser physics. So you have your emission spectrum would have, let's say, in fact, an ultra narrow peak, which is the special feature of this superradiant laser, because this is like the line width is controlled by the atomic line, not the decay rate. There is sharp single peak at zero frequency. But as soon as you reduce the fraction of driven atoms, and you make finite less than 100%, again you see that you have two frequency components, and so this would correspond again of an average over two, let's say, dynamical states with opposite character. You also see that there is a second feature here that if you if you drive less than a critical fraction, you lose lasing altogether. It's not a matter of I just say that this, if you look at finite size effect, you also see that there is a frequency shift, but there is also a broadening of the line width, and there is also a reduction of the power. And this is to say that I think that superradiant lasers are people like them because of the ultra narrow emission, the ultra stable frequency emission, and I think that this shows that as a matter of principle, say, if you don't drive, if you have some imperfections, so for instance, you don't drive exactly all of your atoms, these could have really unwanted consequences for the features that you'd like to have in a superradiant laser. So can, in particular, determine a shift in the frequencies and broadening the line. And finally, there is also a nice connection that we got to appreciate is that this second model implements a model that is inspired from social dynamics. It's a work by Steve Strogatz, where they discussed what is the kind of interaction between, they call it conformists and contrariants. So let's say you have two populations, one population that want to align with respect to the average, so in this case with respect to the average phase for us, and then you have one population that wants to oppose to the average behavior, in our case the undriven atoms, they want to oppose to the average phase. And in the mean field limit, this model exactly recovers this model by Steve Strogatz of conformists and contrariant dynamics. And with that, I hope I managed to partially convince you that non-reciprocal interactions can be engineered between active quantum systems, and this leads, one maybe might have expected from classical states to dynamical, called traveling wave states. This can also emerge out of measuring, continuously monitoring these systems. And then there are also practical consequences that I'd like to explore more, related, for instance, in the case I showed you about physics of superradiant lasers, that are well captured by this notion of non-reciprocal interactions. And with that, I would like to thank you for
Thanks, Matteo. Thank you so much. Questions?
A question about the active method part. Because it's kind of understanding for you, active means that you are gaining the speeds, basically, right? But I mean, one notion of being non-active method is that you have central value particles.
very good.
So is there a connection because these are two different definitions of the active method?
No, these are, let's say, like what I try to say. So in this case, there is no notion of self-propulsion, so there is no kinetic energy to laser hole. But as far as I understand, so the underlying common requirement of active matter is that there is gain activity, call it if you want, of each constituents of your system. So in very practical, so in our model, if I were to replace local gain by collective gain, this would not happen. So let's say a key ingredient is that there is local breaking of detail balance, so if you will. And then classical active matter. I think that the idea is that once you achieve these conditions where each particle is an active particle, then either you can have this out of equilibrium condition determine self-propulsion, or you can have that this out of equilibrium condition can be used to exert non-reciprocal forces typically on the two systems. But in general, yes, I mean, I would say that in some of the cases, the results of being active should be some kind of notion of self-propagation. And again, as far as I know, well, there is a work by Marcus Heil. I mean, I think there are a couple of works, really like 2 or 3 works that try to think about, I mean, even at a single particle level, what is an active quantum particle? And this is, let's say, in a different spirit of what I told now. Nonetheless, I think that is also very, very interesting direction.
Any other question? Yes.
Do you know any kind of stochastic thermodynamics interpretation of this kind of dynamics? On the quantum level?
At the quantum level, no. At the classical level, there has been. So again, I discovered that the active matter community is huge, and